So those are our aims for this lesson. That's what I hope to do over the next 45 minutes. So let's start by thinking about what happens during states of matter. Okay, so there are three basic states of matter. Hopefully you know this bit already, but we're just going to remind ourselves. We've got solid, liquid, and gas. Okay. Now, if we look at, we know the macroscopic properties. Remember, whenever we're thinking about thermodynamics, we have to think about macroscopic properties, the things you can easily see, and the microscopic properties, what's going on with the particles. So solids, a solid material we know has a set shape, okay? Doesn't easily change shape, okay? It's usually dense, and it's usually not compressible. Okay, we know that those are three particular properties, among others, of solids. But we need to know about why that is, because we're sort of going into a deeper level here. So what I need to do is really explain what's going on with solids, liquids, and gases. The basic idea behind a solid is the atoms are bonded together. So they can sort of oscillate a little bit, but as they oscillate more and more, that bond gets a bit weaker. Okay, so let's see how this relates to a change in state. So if I take something like water, now this water is at minus 24 degrees Celsius, so you should have realized by now that this would definitely be ice. Okay, so it's solid ice. If you look, all the particles are actually bonded together. They're not, they're very tightly bonded. So looking at it in terms of my interaction, it's cold, so it's very low energy. Whoops. And they are kind of vibrating a little bit. So there is some energy there, but it's nowhere near enough to break the bonds, okay, between the two atoms or molecules. So that's what happens during a solid. So, and I just realized that I've kind of done that. So I'm going to do that again, but this time I'm going to share my screen. I do apologize. I'm going to share my screen just to show you it again. I'll do the quick version. We've got ice. These are water molecules. They're all kind of bonded together, all stuck together. They can't move. So it's a solid shape. If we look at it in terms of the actual bond between the particles, whoops. Look at it in terms of the bond between the particles, it's as if they're kind of at the most stable state. So the two particles are bonded together, but they are vibrating because they are vibrating because they are kind of they're in a balance between attraction and repulsion, but they're a kind of they haven't got enough energy really to escape. So that's what's going on. So if we go down back to this, we can then start to look at the microscopic properties. We know particles are bonded, okay, with quite a strong bond. We know the particles are close together. Okay, now the fact they're close together actually links to the fact they're not dense, and the fact they're close together and they're bonded would explain why it's very difficult to compress it. Very, very difficult to compress a solid. The fact that the particles are bonded explains the set shape. So that's the basic properties of a solid. Now, as we look now to a liquid, I need to go back to share my screen, and we need to heat up this water to the melting point. At the moment, we are a solid. So as I increase the temperature to make liquid water, there we go, about sort of just a bit above room temperature, you can see that the particles are free to move around. They're still close together. In fact, they're closer together than they were with when they were solid. But that's why ice expands when you freeze water. That's why it expands. But the particles are close together, but they're not so freely bonded. So what's actually happening is, in terms of the actual bonds between the particles, is that they're now a little bit more loosely bonded. So they can sort of separate, and it wouldn't take much to actually separate that particle much further. So they are a bit more loosely bonded. So it enables the particles to move across each other so that they fill the vessel, they only fill the bottom of the vessel, but they can change shape. And that's what a liquid does. So if I make that in some notes for you, we know that we can change the shape. The macroscopic property of a liquid is we can change its shape. We still know that they're dense, almost as dense as solid. In fact, water is slightly more dense than ice, particularly water at low temperature. And we know that because they're dense, it's also not compressible. And I can prove that on my simulation, because I've kind of said that. So let's have a look at why that is. Well, if I go back to my simulation, I could try and compress this water. At the moment, I'm just moving this down. I'm not really compressing anything because there's nothing above it yet. But if I then take this water, if I take this piston and I compress it, I try and compress the water as much as possible, it doesn't really compress very easily. The pressure builds up really quickly for a very small change in volume. Okay. Let's put some water vapor back in there. There we are. Cool that down to below boiling point because we're still a liquid. Okay. Pull it down a bit further. There we are. So we've now got our liquid. The particles can move about over each other. There's still some particles that seem to be able to escape, but we'll come back to that when we start looking at the difference between evaporation and boiling. Right, so what does that mean in terms of how the particle theories can actually explain the behavior of a liquid? Well, the changed shape is because the particles are weakly bonded. Which means the particles are weakly bonded, which therefore implies they can move about. But they're still kind of stuck together. They still have to be close together. Okay. So the weak bonding between the particles is why it changes shape. The fact the particles are still close together because they are still weakly bonded is why it's dense. And the reason why it's not compressible is again because they're all close together again. Okay. So it's the same explanation. Now, with the gases behave in different ways. So if I go back to my demonstration, okay, I heat up this this water to above boiling point. Let's take it well above it just to be absolutely certain that we are making this nice and hot. Okay, and we know that gas molecules, gas particles can move about freely. Okay, so the water's now boiled off. Just going to give it a bit more encouragement. And you can see that they can move about with lots of energy. I might put a bit more in there. So at the moment, it's not behaving like an ideal gas particularly. There we are. So they can move about. They move about at random. They're spaced out. And that's the reason why you can compress a gas to a higher pressure, and when you compress it, when you change the volume, it changes the pressure. Whereas when it was a liquid, if you try to compress the liquid, the pressure built up so quickly the apparatus broke because it's not compressible. So that then explains why gases behave like gases. We all know that gases can change shape. Okay. We all know that it's less dense. We know that gas is compressible. We can compress a gas. So particles not bonded at all. In fact, they move about a lot, quite freely. We know the particles are far apart. And that explains, the fact the particles are far apart explains why it's compressible and not very dense. The fact the particles are not bonded explains why they can change shape. So we end up with three states of matter: solids, liquids, and gases. There is one beyond that called a plasma, but I'm not going to go into that because we don't need it. So we all know, hopefully, that if you take a solid, you heat it up, then it will undergo a process called melting. We know that if we take a liquid and you heat it up, it will boil. We'll come back to that particular part of the process. Now, other parts that you need to be aware of, you need to be aware of some of the other bits of language here. So when a gas becomes a liquid again, it's called condensation or condensing. We know that when a liquid becomes a solid, that is freezing. These happen at particular temperatures. So for example, with water, if you take liquid water, you cool it down to 0 degrees Celsius, it will eventually freeze. So the freezing point is 0 degrees Celsius. If you take ice and you add thermal energy, it doesn't change the temperature, it changes the state into a liquid. And that process is called melting. The temperature at which melting occurs with water at atmospheric pressure is about 0 degrees Celsius. It's the same temperature. Melting point and freezing point are the same thing. Same thing goes with boiling point and the condensation point for any substance. Okay, although we don't usually mention a condensation temperature, we just say boiling point. There is also one more that you might come across, very infrequently asked, but you can sometimes go directly from a solid to a gas, and that's called sublimation. So if I try and demonstrate that on my simulator, here I've got some water vapor. If I decrease the pressure, sorry, increase the pressure, whoops, try again. Put some more in. If I increase the pressure at a very low temperature, so let's take water at a just above boiling point. So just above the freezing point. It takes a few minutes. So it got very, very hot. Right. Now, if I take this water and I'm going to decrease its temperature so that it's ice, okay, but it's under quite high pressure. Okay, I'm going to take it just a little bit below. Whoops. I'm suddenly going to release the pressure. It should, it didn't quite do it properly there, but what it should do is it can actually sublime, because when you have water at very, very low pressure, it can actually evaporate straight from a solid to a gas. Dry ice is a good example of something that does do that, so I apologize about that not quite working the way it should. Let's just move on, I think. So we understand a little bit about what happens during changes of state. Now, if you think about it, what have you got to do when you're changing state? Well, one of the things you need to do when you're changing state is you need to do something with energy. Okay, so for example, as I said before, a solid is where where the particles are very firmly bonded together. They can still vibrate, as you can see. They can vibrate quite a bit, but in order to turn into a liquid, you've got to add a little bit more thermal energy. Now, as you add that thermal energy, you increase the vibration so that the particles become less, vibrate a lot more. So that's where the energy is being stored. But what also happens is that they become less well bonded, and you get to a point where they're very, very weakly bonded. They can actually escape from each other to a certain extent. And now, in order to do that, you could see I had to put some energy in. I had to move the particles apart to do that. So in order to take a solid and turn it into a liquid, I need to add energy. Okay. Oh dear, it's not shared. I do apologize. I'll just show you that again. I apologize. Seem to be having a few technical problems today. So you can see that as that's a liquid, I've added energy, whereas a solid, there's less energy. So they vibrate a little bit, and the more you make them vibrate, the more energy you give them up to a certain point is where you start to break some of those bonds. You start to weaken the bonds, and you need to put energy in to do that. So let's show you that bit. So the next thing to do really is to talk about the changes in energy. So when you change from a solid to a liquid, you've got to add energy. So what happens when you change state is you must add more energy as you change state. So for example, you have a solid, a liquid, and a gas. So when you want to melt a solid, melt some ice, you've got to put some energy in to change it into a liquid. Now, this energy doesn't heat the ice up. All it does, doesn't increase its temperature. All it does is make it change state. So it's like a hidden form of energy, which is called, and you'll come across this with Mr. Welsh, latent heat. Okay? So as that's latent heat, it means it's hidden. The word latent means hidden. Okay? So as we then take a liquid, we heat it up and we increase its temperature up to the boiling point. Then we get to the boiling point, what happens is that the bonds then, further bonds will then start to break. You need energy to break those bonds. Because you need energy to break the bonds, the temperature of the liquid doesn't increase, but it will change into a gas, okay, beyond a certain temperature. And that's down to, if I go back to my simulation, the idea that if I add more energy, then the bond is so weak that it's no longer an attractive bond anymore, okay? In fact, I'm just going to demonstrate it a little bit more clearly than that. Give it a bit more energy. The particles can actually sort of separate out, okay? Now, go back to my notes. There we are. So that's what's actually happening when things change state. You're breaking bonds, which means you need to put energy in, okay? Now, if we want to go in the other direction, then the energy goes in the other direction too. Okay? So what actually happens is if we take a gas and it condenses, it gives out a little bit of thermal energy as it does so. It doesn't change temperature, but it gives out some thermal energy. Same thing goes if we go from a liquid to a solid. You change state from a liquid to a solid, it gives out a bit of thermal energy. That's how some of those chemical hand warmers work. You can buy hand warmers where you click a little button inside a little pouch of liquid, it becomes a solid, and in doing so, it actually does give out some energy, and so it feels warm. Similarly, if you're changing state from a solid to a liquid, then it helps to cool things down. That's why ice is better at cooling down a warm drink than water at 0 degrees Celsius, because some energy is required to actually melt the ice and it takes it out of the warm drink. Same thing goes in boiling. When you boil something, when water evaporates, for example, then it takes energy away. As it takes the energy away to evaporate, it feels cool. And that's why when you do a lot of exercise, you sweat, your sweat evaporates and you feel cooler, okay? In this particular example, condensing, that's quite useful too. When water condenses, or when any gas condenses back to a liquid, it gives out some thermal energy. This is used in boilers for heating systems, and I'll show you that in a minute. When you can use the fact that water vapor is given off when you burn natural gas, make it condense on some cold water pipes, and as it does so, it gives thermal energy to the water before the gas actually heats up the water itself. Okay, and that's how some boilers work. It's also a thing to remember. If you ever put your hand in some steam, you can get some really nasty burns if you put your hand in steam rather than just the bit you can see. The water, that's just condensed water vapor. The bit you can't see when you're boiling water is just above the boiling water surface, which is like a clear layer, and that's actually water. That's actually proper water vapor. If you put your finger in that, you'll burn yourself really quite badly because it'll condense onto your finger. So don't do it. So those are some of the ideas about changing state so far. We have described why solids, liquids, and gases have their properties. We've described what happens during a change in state, and I'll come back and teach you a little bit about latent heat later on. So the last bit to do is to look at explain about the difference between evaporation and boiling. If I boil water, boiling implies raising the temperature to boiling point and then you add thermal energy. Add thermal energy to boil the water to create the change of state from a liquid to a gas. Okay. So, for example, if you take a kettle, there you go. There's your kettle, a spout. And you take your water. What happens is the heat in the water takes the water to 100 degrees Celsius first. Then 100 degrees Celsius, you get your little sort of bubbles of water forming and you get your steam your water vapor produced. Okay, so that's what happens when a kettle boils. But water evaporates. And it does so below 100 degrees Celsius. Okay, so for example, if you get a t-shirt, okay, and you make it wet, eventually the t-shirt, if you hang it out on a warm day, eventually it will become dry. Okay, and that can happen at 20 degrees Celsius or even lower sometimes. So, which is quite useful, because if we've got something that's wet and we want it to just dry naturally, to just sort of to dry off, we can leave it out to dry it. We don't have to raise its temperature to 100 degrees Celsius to boil off the water. But that creates a problem. How does that happen? Well, this is the difference between boiling and evaporation. Boiling, you take water up, you take a liquid up to its boiling point, you create the bubble, it then all wants to evaporate pretty much at the same time as you're adding the energy. Evaporation happens at a lower temperature, and it's down to the volatility of the liquid. A volatile liquid basically is one that will evaporate quite easily. So I'm going to go back to my demonstration again. Let's go back to it, because there's something else I can show you now. So if I go to my states of matter, at the moment I've got solid ice, okay, minus 58 degrees Celsius. And what I'm going to do is I'm going to turn it into liquid water. So here we've got liquid water, and you can see the particles are not quite so tightly bonded. But as I heat it up to sort of a warm summer's day, let's have a hot summer's day, about 30 degrees, a little bit on the hot side, you start to see something happening over here. You should start to see in a minute a couple of these particles actually being released. Okay, I'm going to give it a little bit of encouragement. Okay, it's a very hot day, in fact. There we are. You can see that some of these particles are actually escaping. They're escaping below the boiling point of the water. So if they're escaping below the boiling point of the water, something must be happening. We're not breaking laws of physics. So let's have a look at that. So it makes sense. Remember, one of the assumptions, we make 5 assumptions about gases. One of the assumptions is random motion at a range of speeds. Okay, so if we were to take a particular gas and we were to look at the number of particles, and we're going to look at the kinetic energy. Okay, what we would get is a range of what's called a Boltzmann curve. I'm not going to draw it too accurately, you don't need to know too much about this, but this comes in quite handy. We get like a range, okay? We get a bit of a peak. Now, what happens is if this is, say, water at, this is water at maybe 50 degrees Celsius. If we take water, the same amount of water, and we have it at a lower temperature, then the average kinetic energy, the peak kinetic energy, if you like, will be slightly lower. So it might be something like that. So maybe that would be at 10 degrees Celsius. Let's assume it's water. Now, we know from our simulations that if you take the 2 bonded atoms and you give them a little bit of energy, then that bond gets a bit weaker, they vibrate, which is what we expect. But we know that if you give this atom enough energy, a higher amount of energy than the energy of the bond, then it will be released. Okay, and it's down to the kinetic energy and potential energy of those particular atoms. I should say energy rather than anything else. But does that make sense? Well, let's have a think. If I give it more energy, anything with above a certain amount of energy will quite happily escape. Okay. Didn't share it. Sorry about that. Let's try it again. Anything with enough energy will escape. So if we go back to our graph, if we're thinking about it, what we could be thinking about here is that if that there is the maximum available sort of energy, after which anything beyond that energy, that threshold, actually escapes, what will happen is that the gas, that any particles beyond here will escape. Okay, they escape. So those particular particles will escape. Now, if we think about it, if we were to liken it to sort of the square speed or the mean, or the sort of mean square speed, so to speak. Okay, we know that would imply the gas has a mean square speed, which we know is proportional to absolute temperature. Now, if we think about it, we could say, for the sake of argument, that you have a gas with 5 particles. One's got a speed of 100 meters per second. The other one's got a speed of, say, 200 meters per second. The other one's got a speed of, another particle has a speed of 300 meters per second. And the other one has a speed of 200 meters per second. Okay, now what we would do is we could work out the mean square speed. So if you wanted to work out the speed squared, that's 100 squared, that's 10 to the power of 4. That's 4 times 10 to the power of 4, 9 times 10 to the power of 4, 4 times 10 to the power of 4. So we add them together, that's 1, 5, plus 9 is 14, plus 4 is 18. 18 divided by 4 gives you a mean square speed. Alexa, what's 18 divided by 4?
18 divided by 4 is 4.5.
So 4.5 times 10 to the power of 4. That gives you the mean square speed. So that would correspond to a particular temperature. Now, let's say that one evaporates. Let's say that particular particle is moving so fast that it actually, it's got enough kinetic energy that it can escape. Okay, it's got a certain amount of energy. Now, if that's the case, it evaporates. So that would then be an average. Instead, if that one escaped, an average would be 1, plus 4 is 5, plus 4 is 9. So we end up with 9 over 3, which is 3 times 10 to the power of 4, which is the mean square speed of the remaining particles. Now, as that's lower, then it's going to imply a lower temperature, if that makes sense. So the idea, it's not all kinetic energy movement because it's a liquid, so it's a combination of kinetic and potential energy. I've just used kinetic energy really to try and simplify it a tiny bit. So what it's saying is that any particle with above a certain threshold energy and will happily evaporate because it'll overcome the bonds between the actual particles. So if you have a liquid at a particular given temperature, all the particles will have different amounts of energy because the energies are sort of over a range. They don't not all the particles have exactly the same amount of energy. Because of that, particles with the highest amounts of energy will have enough energy to break the bonds, such that the original temperature would be higher than it was after one of the particles evaporates. And that is why when you sweat, you feel cool, because what happens is the average energy and therefore temperature of the sweat remaining decreases. And that's the reason why evaporation cools. The big difference between evaporation and boiling is with evaporation, it happens below the boiling point. Obviously, the higher the temperature, the more evaporation will occur over time. But because its actual temperature is below the boiling point of the liquid, it's just that some of the particles have enough energy to escape the bonds that are in a liquid and therefore will evaporate. The same thing, the different idea with boiling is that all the particles are given enough kinetic energy, enough energy to actually overcome the bonds, and therefore they all evaporate. Obviously, each time you need to put energy in, which brings me into something that's probably very similar to what Mr. Welsh has shown you. And that's the idea that if you want to change state, you have to add thermal energy. What the concept here is latent heat. Mr. Welsh will talk to you a little bit more about latent heat, but the basic idea is very, very simple. The idea is that if you want to put in a certain amount of energy, if you've got water at 100 degrees Celsius, you need to put some energy in to make it change state. And the more energy you put in, the higher the mass of water that will change state into steam, let's say. So it's multiplied by some kind of constant, okay? So that's the basic idea behind the concept of latent heat that Mr. Welsh is going to describe to you. The whole purpose of this is to actually understand that you need to add energy to change state. So this is what's called the specific latent heat. Now there's two of those, one for changing from a solid to a liquid and one from changing from a liquid to a gas. It's called the specific latent heat of fusion, which is changing from a solid to a liquid, and specific latent heat of vaporization is changing from a liquid to a gas. So the specific latent heat of fusion and vaporization is the amount of energy required to change state now. Just like here, you've got the fusion, you've got vaporization. So fusion would be change state from a solid to a liquid. Or for vaporization, it would be from a liquid to a gas. Whoops. From solid to a liquid or liquid to a gas. Now the important bit is it's without a change in temperature. Okay, so the idea would be that if you were to watch something cooling at a constant rate, you'd see it first of all as a liquid, and then as it's solidified, it wouldn't change temperature until it's become a solid and then cools down again. And during that bit there, that bit is solidifying or freezing. Okay, So that for water, for example, that would be 0 degrees Celsius.
First lunch sitting. Students in non-practical classes should go for lunch and return in 45 minutes.
Okay, so that is the basic idea behind freezing, behind the change of state. What's happening is that the liquid is losing thermal energy at constant rate. As it changes state, it's still losing thermal energy, but that loss of energy is causing a change of state from a liquid to a solid. And then once it's all become a solid, it then cools further by changing temperature. So that's the basic idea behind those different states of matter. I hope that's helped. Arda, have you been okay with that? Okay, I'm assuming Arda can't hear me, or was just put his Zoom screen on to make me think I'm talking to somebody. But I'll stop it just there. Second half of the lesson, if you go back to show my homework, you will see that there is some more practice questions to have a go at. I need you to practice those practice questions. I can't stress this enough. If you don't practice the questions, to put it very simply, you're going to really struggle when it comes to the exams in June. You are faced with exams in June. You do need to take part in them. So I will stop you there and I will see you next time. Please have a go at that task I've set you on Show My Homework, and please do submit it. Thank you.